Dear students, welcome back to the operating system lecture video schedule. In this lecture video, we are going to continue the previous topic, process concept. In the previous lecture, we have discussed about process concept, process in memory, different process states, process state diagrams, and process control blocks we have discussed. And we have also discussed about state representation in Linux. So in this today's session, we are going to learn about process scheduling. In this process scheduling, we are going to discuss about what is process scheduling and what are the different schedulers we will discuss. So process scheduling basically maximize CPU usage and quick switching process onto CPU for time sharing. So every process will be having its own particular time. Right. So for this, to make each and every process in a schedule, we are having process scheduler. This process scheduler selects among available process for next execution onto the CPU. So generally, it maintains CPU scheduling queues of process. Generally, these queues are job queues, ready queues, and device queues. There are three different queues. What is a job queue? Job queue set all processes. Job queue set all process in the system, and ready queue sets of all processes residing in main memory and ready for waiting to execute, which are ready to execute, that will be stored in ready queue. And device queue, what it is going to maintain? Set of processes waiting for an IO devices, and process migrates among various queues will be stored in device queue. So generally, the process migrates among the various queues, one queues to another queues, job queue to ready queue to device queue, like that. That process will be migrate. So ready queue and various IO devices. If you see here, this is this is a ready queue. Here you can check. This is a ready queue, and ready queue is containing different PCBs, process control blocks, PCB2, PCB7, like that. And this is device queue. Magnetic tape is a device. Magnetic tape unit 1, unit 0. This is disk 1. This is terminal unit 0. So these are all device queues, and this is ready queue header. So this generally it is in a linked list. It is using the linked list. Internal one part or another one, it is going to use its head and tail, and then that will be connected to another node. So representation of process scheduling. How we are going to represent this process. So here, this queuing diagrams represent queues and resource and how it will flow. So generally, your CPU will always search from the ready queue. If the process in the ready queue, if there is some process in the ready queue, that means that it is going to utilize the CPU to complete its process. For in case if there is a process which needs some input output device, for example, it needs this printer, needs a printer, then printer is already busy, then that process will be sent to the IO queue, and this IO request will send to the IO queue. If it needs a printer, then here is the IO devices, and this is going to allocate that particular printer. If the printer is available, then that will be sent to the ready queue. Then whenever it comes to the ready queue, then that will be sent to the CPU again. In case if, and remember, each and every process will have its own time slice. For example, each process in your CPU, if it is allocated with 5 microseconds, if that process is unable to complete within that 5 microseconds, then that will be sent to here. That is, the time slice is expired. Whenever it is expired, then it will come to the queue, and after when it comes again, then it will go to the ready queue. From that ready queue, again it will send to the CPU. If it is dependent on its child process, it needs to create a child process, then it will do a fork process, that is creating the child process. Then the child will get executes. Whenever that child executes, then that will be sent to the ready queue again, and whenever it is in the ready queue, then that will be sent to the CPU. If it is stopped with any interrupt, either IO device interrupt or memory interrupt or something else, if there is an interrupt, then till the interrupt clears, then it will wait, and interrupt cleared, then it will send back to the ready queue. From there, again, it will be sent to the CPU. So this is what generally happens in your process scheduling. Right. So in order to make your ready queue, scheduler will work. So here there are several types of schedulers. One is short-term scheduler, long-term scheduler, middle-term schedule is also there. So we'll see one by one. Short-term scheduler. What is a short-term scheduler? It just selects which process should be executed next and allocate CPU. What is the process to be allocated, and that will be sent to the CPU. Sometimes the only scheduler in a system, right? If there is no processes. Then short-term scheduler is invoked frequently, continuously. Basically, first short-term scheduler will be completed because it is very fast. Short-term scheduler is very fast. So first CPU will approach the short-term scheduler. Then there is another scheduler called a job scheduler or long-term scheduler. So in long-term scheduler, which selects processes should be brought into the ready queue, then only it will be sent to the CPU. Long-term scheduler is invoked infrequently, not frequently, right? Infrequently, it will be just like once per a minute or once per a second, like that. It is very slowly it will be selected. If there is no jobs in the short-term scheduler, then sometimes CPU will go for the long-term scheduler if there is anything, right? Long-term scheduler controls the degree of multi-programming. Long-term scheduler controls the degree of multi-programming. What is degree of multi-programming here? So what is degree of multi-program? The degree of multi-programming describes the maximum number of processes that a single processor system can accommodate efficiently. Means a single processor, how many processes it is completed in a particular time. So this is called as degree of multi-program. There are some of the factors affecting the degree of multi-programming, such as the main factor is amount of memory available to be allocated to execute the process, right? Well, that is one of the factor. The degree of multi-programming is a processor within a stipulated time, how many process it is completing, how many process is executing successfully. That is called as degree of multi-programming. So generally this long-term scheduler controls the degree of multi-program, right? Process can be described either IO bound process or CPU bound process. What is this IO bound process? IO bound process spends more timing doing IO, more timing doing input output devices than computation, right? So whereas CPU bound process, it spends more time on doing computations and few very long CPU bursts. CPU bursts are very long. So long-term scheduler strives for good process mix. So there is not proper process mix for the long-term scheduler. That is the main drawback of a long-term scheduler. So addition of medium-term scheduler, long-term scheduler, short-term scheduler, and this is medium-term scheduler. So medium-time scheduler can be added if degree of multi-program need to decrease. If you want to decrease the degree of multi-programming, then we can go for the medium-term scheduler. So what it is going to do, it is going to remove the process from memory, stores on disk, and bring back from the disk to execution. That means from the CPU to disk, and it will take from CPU to disk, again disk to CPU. So that is moving from here to there to here, right? That is called as swapping. This swapping, students, you are going to learn about this swapping in unit 3 in detail. Okay. Okay. So this is generally happens when the job is in ready queue. Job is in ready queue, that will be sent to the CPU immediately. Sometimes that process needs more memory than whatever it is having. Then that process, particular process, will be kept out, will be removed out from the CPU, and that is called as swap out. Then whatever that partially executed, why it is swapped out, and if it needs some resources, that will be given, the resources will be given, and that will be swapped in, that will be swapped into the ready queue. Then it will be sent to the CPU. That is the first way. If that process is waiting for any IO devices, if that process is waiting for any IO devices, then that will be sent to the IO device queue. And whenever this IO is allocated, input output device is allocated, that will be sent to the ready queue. From ready queue to CPU, it will move. Then after completion of CPU execution, then it will be sent for end. That is, the process will end here, right? This is medium term schedule. Right. Multitasking in mobile systems. Some mobile systems, generally iOS versions, early iOS versions, allows only one process to run, others suspend. Right, the remaining process will not be done. This is an older version, not the exactly your mobile phones, whatever you are using now. So due to the screen real-time, real status user interface limits, iOS provides for a single foreground process. That means in the foreground, you can see only one process is running that will be controlled by a user interface. And multiple background process in memory running, but not on the display and with limits. So maybe some applications are running in background, but that you cannot check it. That there is the reason here is that limits include single short task or receiving notification of events, specific long running tasks like audio player. These are the very limited applications may run. Coming to Android runs foreground and background with fewer limits. Guys, I'm telling you about the older version, not the exactly mobiles what you are using. So background process uses a service to perform tasks. Service can keep running even if background process is suspended, and service has no user interface. Small memory will be used. Right. The next one is context switching. When the CPU switches from one process to another process, then it have to save the status of process one, and when it is sending to the process two, then it have to fetch the process details status, and then after completion of its execution, it have to save the process status, and then it have to move to the process one. So whenever your processor is moving from process one to process two, that is called as context switching. So this context as a process represent in the process control block, and generally the more complex the OS and the process control blocks, the longer the context switch. Whenever it is longest context switch, then it will be more complex. Some hardware provides multiple sets of registers per CPU, then it is multiple context loaded at a once. So this is all about the contents of this video. In the next video, we are going to learn about inter-process communication. Inter-process communication. Thank you. We'll meet in the next video.